What's up, guys? Back at it again. Um, it's May 21st, 2 p.m. And then this is the daily question 73 set matrix zeros. So if an element is zero, then you set its entire row and column to zero. A straightforward solution would be to um go through element by element. Um, OM times n, right? So go through element by element, and then you check if that row or that column has any zeros. A simple improvement uses OM plus n, but still not the best solution. Can you devise a constant space? Mm, What would I do here? Mhm. So I'm thinking four, right? And then another four. So this is the row, and this would be the column. But is this necessary? Okay, so I'm thinking, is this a DP question? I'm thinking. No? Okay, whatever. So I'm thinking, um, yep, I'm thinking of this. So void unordered set int, and then this would be rows. And then another one of these would be column, right? And then for int I smaller than m, and then int j is smaller than n, plus j. And then if, let's say, rows dot contains I. So if the rows set does not contain I, right? I think it's contains, right? Contains, yep. If rows does not contain I and row and columns does not contain J and matrix IJ is equals to 0, right? Because if it already contains, then I don't even need to check it, right? Um, then I don't even need to check it. Then rows dot insert I, columns, you will insert J. Ah, but this creates a problem, right? So I'll only check this. What's up? 有冇? Or I can reconstruct the matrix entirely. Oh, but I have to do this in place, huh? What is a quicker way to do this? Because if I check the first one and I insert columns and rows, then this will not be checked. Or I can check all of them. What is the cheese here? What is the cheese? Okay, so using that, so I'll have a vector of bool, right? Row of of matrix dot size, right? These are amount of rows that I have, and then they would all be false. And then this would be columns, matrix 0 dot size, and they would all be false. If true, row is set to 0, right? If true, column is set to 0, right? Okay. And then I'll do this. And then if rows I is equal to true, no, is if it's false, then I'll set it to true, right? If it's true, but if it's false, right. And then after this for loop, I'll have another for loop. Um, right, this will be a very stupid and slow solution. That's the whole thing we're trying to avoid, right? What? I mean, this is just redundant, but I don't think it like hurts necessarily. Or right, but for sure this will hit the time limit. Oh, it doesn't hit the time limit actually. The fuck? Oh, okay. Okay. So what I'm doing here is right, one vector to track which one is false, one vector to one vector to track which row is set to false, is set to 0, and then one vector to track which column is set to 0, and then I iterate through all the elements, and then if the element is 0, then I'm setting that row or that column to true or false, right? Then if it is 0, then I'm setting that row to 0, and then I'm setting that column to 0 as well. Um, this does not have to be done for every single uh element. Like I can add extra checks here, so it's not as redundant, but it doesn't matter, I guess. And then I'm doing another nested loop to loop through all the elements, and then to check if that row has been set to 0, or if that column has been set to 0, then I will make it 0, right? But this is an OMN solution, OM times N time complexity, which is what we want to avoid, right? Um, Here, a straightforward is probably a bad idea, right? It is a bad idea. Um, OM plus N. Uh, so I'm thinking if there are quicker solutions here. We're still dealing with a double nested loop. Okay. But it's just it's with constant space, right? But the time complexity is still kind of ass. What is the what is the time complexity of the solution? M times N, right? Yeah. But this solution will be N times N as well. I want to see M plus N solution. Owen space, sure. Everybody doesn't m times n solution. Where's m plus n solution, bro? Where is it? Space. Oh, space. Okay, I get it. So the time doesn't actually matter. Okay, so it will be something like this, right? So it is m plus n space. O1 space will be the best. But it's all right, I guess. Constant space. Let's see the constant space solution. Let's see how much better this performs. Yeah, a little bit better. It is a little bit better. 5214. Oh, it's literally the same. It's a bit better. It's a bit better. Okay, sure. I am happy with that. I am happy with that. Okay, so it's not that difficult. It's not medium, you know, it's not medium level difficulty. I was thinking, how do you do this with constant time, linear time, right? But I guess everybody does it uh, this way, so it's whatever. Yep, so that is part of the leak code done today. I really want to finish Unit 4 today, but this is giving me a lot of trouble, to be honest. Like, I don't really understand what's going on. Um, One thing that I do understand is like like the ISA meaning the architecture. Um, the instruction set architecture, right? The architect will define the ISA, right? It gives it a bunch of bits that defines what the CPU does. Sorry, so so what I'm thinking is essentially this, right? Let's say, no, you know what? This illustrates it quite perfectly. Like, what the fuck is this? Okay, this.
This is the single greatest achievement of my life today.
Respect, bro.
But it's a massive.
But this, this is essentially what's going on, right? You're defining what codes, so what bits you flip, define, you're defining which codes represent which operation, right? That's what I believe it's doing. Um, so for example, like 0000 might mean the number 0, right? And then 0001 might mean the number 1, for example. And then et cetera, et cetera, et cetera. Um, yeah, the clock stuff, I don't really understand still. Um, this I understand. So like x86 is one architecture of CPUs, right? And then ARM might be another architecture of CPUs. Okay. In that case, it refers to baseline ISA, i.e., actual standard set of instructions that gives CPU can understand. Registers. This can sometimes be meant in more narrow sense of what extensions give CPU supports. Internal implementation of those can be called architecture but usually and more accurately microarchitecture. In particular, modern CPUs tend to have largely identical external set of instructions they understand, but deep down internally, the exact way they're decoded and handled can change dramatically. Okay, that I understand. This is what people often mean when they say that RISC, CISC distinction is meaningless for modern CPUs. Think Intel Skylake and AMD Zen being different architectures despite using largely the same ISA. Okay, so the codes that they run are the same. The operations they understand are the same. However, how they're actually delivered and implemented within the CPU is different. That's what I'm understanding, right? Most broadly and probably least applicable are RISC, CISC are even more generally von Neumann architecture. This is largely just theoretical talk relevant to computer science or discussions of a long-term future of computing. ISA is the contract between hardware and software. If a CPU implements an ISA, it will run all software for that ISA. Okay. If software is encoded for an ISA, it will run on all CPUs implementing that ISA. Sure. Microarchitecture is the design of the CPU, right? Okay, I understand. Ryzen, Alden Lake are different microarchitectures. Different microarchitectures. They are the blueprint of a CPU implementing an ISA, but they have been designed by different teams at different companies. Okay, so like for example, Ryzen, Alder Lake, their physical design is different. However, they understand the same ISA, right? Right. Think of an ISA as a language. You can have different ways of processing it. The language has some implications on the architecture used to process it, but the exact mechanisms aren't necessarily defined by the ISA. Okay. x86 is an ISA. Currently, Intel makes Skylake processors, AMD makes Zen processors. They both support handling these instructions. Sure. They'll both have certain registers, branch predictors, ALUs, and whatnot. But that's like saying a road-going vehicle has doors, windows, and wheels. One could be a bus and the other could be a race car. I apologize to any CPU engineers. My simplification may have harmed. Okay. The ISA is the front end, right? It's the language that the CPU actually processes. The microarchitecture is the actual hardware, right? Mhm. Right. So x86 has its own ISA. ARM chips has its own ISA. MIPS has its own ISA. Okay, so all of these have their own ISA, right? Right. So this would be like the CPU design. So this would be the micro architecture. Hmm. Understood. Okay. That part I understand. Okay. Um, and then what exactly am I trying to understand here? I don't even know what the question is.
Instructions perform mathematical operations. Add or 1 or 2 adds the value in register R2 to R1, while subtract R1 or 2 subtracts R2 from R1. The multiply and divide instructions perform multiplication and division respectively. Logic instructions handle bitwise operations. End R1 or 2 performs a bitwise end, where only bits that are 1 in both are 1 and R2 remain 1. Or R1 or 2 performs a bitwise OR, setting bits to 1 if either register has a 1. Exclusive or 1.
I kind of want to know what the division logic gates look like. Oh wow, it's a lot of shit. And I mean, I see.
1 and 2 performs an exclusive OR, resulting in 1 if the bits differ. The not instruction alternates the bits in a register, changing ones to zeros and vice versa. Control instructions direct program flow. Jump label causes the program to jump to a specific point labeled in the code. And compare R1 or 2 compares the values in R1 and R2. Based on this comparison, jump if equal jumps if the values are equal, while jump if not equal jumps if they are not. Data movement instructions transfer data. Move R1, R2 moves data from R2 to R1. Push R1 saves R1's value onto the stack, and pop R1 retrieves the last value from the stack. Finally, bit manipulation instructions include shift left, which shifts registers bits left, essentially multiplying the value by 2, and shift right, which shifts right, dividing the value by 2. Rotate left and rotate right rotate bits left or right, looping them back around. These instructions allow precise control over data, arithmetic, and program flow in assembly programming. Keep in mind that there are even more instructions available in assembly, providing further capabilities for developers. Now, let's take a look at how assembly is executed. Assembly language is executed through a process known as the fetch decode execute cycle, which is fundamental to how a CPU operates. This cycle consists of 3 main stages: fetching, decoding, and executing instructions. During the fetch phase, the CPU retrieves an instruction from memory, typically pointed to by the program counter. For instance, if the instruction is shift left or 1, the CPU fetches this command from memory. In the decode phase, the CPU interprets the fetched instruction, determining what action is required and identifying the involved operands, such as recognizing that it needs to shift the bits in R1 to the left by 1 position. Finally, in the execute phase, the CPU carries out the operation as specified by the instruction. In our example, it shifts the bits of R1 left, effectively multiplying the value by 2. This cycle repeats for each instruction in the program, allowing the CPU to process commands sequentially, whether they involve arithmetic calculations, logical operations, or control instructions. By understanding this cycle, we see how assembly language directly translates into actions performed by the computer's hardware, connecting human-readable code to machine-level execution. Now that we've learned about the basic instructions and how they are executed, let's take a look at a practical code example. In this assembly code,
What's that? What's
Coming.
okay?
Everything.
咩意思啊？
我們睇什麼 chapter？
咁正？我做完我呢 code 啦，我而家做緊其他嘢。
It's gonna be my second time rerunning everything.
Beautiful.
Oh my god. This is a lot easier than physics. Oh my god. And it's
Oh,
a lot
really?
easier to lock it. Oh my god.
呢個係咩 networking 啊
Like
？Easy
the
money 啦
so easier.
，easy money 啦。Okay, see you. Okay, goodbye. Bye, peace.
example, we start by loading the values 5 and 10 into registers R1 and R2 respectively. The add instruction then combines these two values and stores the result in register R3. To determine whether the result is even or odd, we perform a bitwise AND operation with 1 and store the outcome in R4. The AND operation effectively checks the least significant bit of the sum. If it's 0, the number is even. If it's 1, the number is odd. Initially, we assume the result is odd by loading this string into register R5. We then compare R4 to 0. If they are equal, we should some weird programming languages of assembly. Assembly language may seem low-level compared to modern programming languages, but it plays a vital role in many real-world applications where performance and precise control over hardware are crucial. For example, it is commonly used in embedded systems, like those found in cars, medical devices, and household appliances, where efficiency and direct control over hardware resources are essential. Game consoles and graphics programming also utilize assembly for optimizing performance, and making the most out of its programming also utilize hardware resources are essential. Game consoles and graphics programming also utilize assembly for optimizing performance and making the most out of hardware capabilities. Additionally, assembly is critical in device drivers, which act as the interface between hardware and the operating system. Even parts of operating systems themselves, especially those that need to interact directly with hardware, are often written in assembly. By using assembly language, developers can fine-tune programs to run as efficiently as possible, which is particularly important in resource-constrained environments or performance-critical tasks. Lastly, let's discuss the limitations of assembly. While assembly language offers significant advantages in terms of performance and control over hardware, it also comes with notable limitations. One major drawback is its complexity and verbosity. Writing code in assembly requires a deep understanding of the underlying hardware architecture, which can be daunting for many programmers. This complexity leads to longer development times, as even simple tasks can require extensive lines of code compared to high-level languages. Additionally, assembly is not portable. Code written for one architecture typically cannot run on another without significant modifications. This lack of portability makes assembly less suitable for large-scale software development, where flexibility and maintainability are essential. Furthermore, assembly lacks the rich libraries and built-in features available in high-level languages, limiting its use in modern software applications. Overall, while assembly is powerful for specific tasks, its limitations can hinder productivity and adaptability in the fast-paced world of software development. In conclusion,
Okay, I understand. Understand. So basically, it's an interface between hardware and software, right? The part that I don't understand is so basically whoever built the chip, the microarchitecture of the chip, for example, x86 or ARM or whatever, that chip like the guy who built the chip will define the ISA. And the ISA is basically the assembly, right? If I'm not mistaken. Is ISA the same as assembly? right? I say is, right? I say equals machine code equals assembly, right? Instruction set is the set of all instructions the processor can execute or understand. Assembly language is a programming language. Let me try some examples based on some of the questions you are asking. And I'm going to be jumping around from processor to processor with whatever code I have handy. Instructions or opcode or binary or machine language. Whatever term you want to use for the bits, bytes that are loaded into the processor to be decoded and executed. An example. In this case, that means R11 equals to R11 plus R12. So you add register 11 with register 12. Assembler, a program that assembles assembly language to assemble it into some form of binary. Like any programming language, sometimes you create object files and link them together. Sometimes you go straight to binary. And there are many forms of binaries which are in ASCII and binary forms or a whole nother discussion. Now what can you do in assembler that is not part of the instruction set? How do they differ? Well, for starters, you can have macros. Okay, so you're just stringing shit, right? So I might use them to save some typing. So you're just abstracting stuff. Yep. hmm What? The reason why there is no pop is because the addressing modes are flexible enough to have a read from the address in the source register, put the value in the destination register, and increment the source register by a word. What the fuck? I don't understand the jump between those two, right? I don't, I, yeah, it doesn't really, Another difference between an instruction set and assembly language. This is assembly. Fuck. I don't get it.
Some difference that enables most of what very limited. I was literally adding new operation codes on a spreadsheet when I implemented it. For my full-scale computer, I wanted to implement a real-world instruction set. I don't have time to go into exactly what this means, but it's a massive difference that enables most of what I've done. But it involves far more work ensuring complete compliance with strict standards. Finally, performance-wise, my prototype is pathetic. My target for the assembly, a low-level programming language designed to simplify the instructions fed into a computer's CPU. In other words, it's a human-readable abstraction on top of machine code, so programmers don't have to manually count ones and zeros. The first assembly language was created by Kathleen Booth in 1947 for the all-purpose electronic computer. Over the next decade, it evolved into many different formats to power the supercomputers of the day, like the IBM 7090, which had a $20 million price tag in today's dollars. Writing code in assembly was standard until the emergence of
high-level languages like Fortran a few years later. However, assembly is still used today for direct access to the bare metal hardware and to address low-level performance issues, often on device drivers and embedded systems. And it's also used to run native software in a web browser via WebAssembly. What's tricky is that systems, and it's also used to run native software in a web browser via WebAssembly. What's tricky is that each assembly language only works on a specific CPU architecture, like ARM for Apple Silicon, Raspberry Pi, or x86 for Intel chips. To get started, you'll first need an assembler, like the NetWide assembler for x86 chips. An assembly program is divided into 3 sections. The text section contains the actual logic for the program. By convention, it contains an entry point called start, which is where the code will start executing. Next, we have the block starting symbol section, which contains variables that might change throughout the lifecycle of the app. And finally, the data section is where we can initialize constants or data that does not change. To declare a constant like a string, we start with a label, then use DB for define byte to of the app. And finally, the data section is where we can initialize constants.
Machine code.
Or data that does not change. To declare a constant like a string, we start with a label, then use DB for define byte to place the hello world string into memory. By itself, it doesn't do anything, and to print it to the standard output, we will also need its length. We can use equate to convert a symbol into a constant. The $sign will subtract the current position from the hello label, providing the length of the string. And now these constants can be referenced from the start label. In the main program, each line of code contains an instruction along with one or more operands, and there are hundreds of instructions built into the language. Now, to perform operations quickly, the CPU has a limited number of registers, which are like 64-bit chunks of memory built directly into the CPU instead of the RAM. We can insert data into a register with the move instruction by providing operands for the register name and the data to store there. In this case, number 1 is used because it corresponds to system write on Linux. Next, we need to tell the system where to write, in which case we'll move 1 into the RDI register, which corresponds to the standard output in the terminal. The next register stores the message to write along with its length. Now execute the code stored in the CPU by calling the operating system kernel. Almost done, but we'll get a segmentation fault if we try to run it at this point. Update the RAX register with 60 for system exit and provide an error code of 0 for success. Now use the assembler to compile or assemble your code into an object file, then use the linker to convert it into the final executable. This has been assembly language in 100 seconds. If you want to see more short videos like this, hit the like button and subscribe. Thanks for
What the fuck?
Every modern computer, when you get right down to the bare metal, is doing basically the same sort of thing. I've said before that computers are just overgrown calculators, but how do you go from a simple calculator to playing video games or sending stuff over the internet or even decompressing and displaying the millions of pixels in this video? In short, what's your computer actually doing? Behind me is a scaled-up version of a computer, but we're going to go much, much simpler. If you take apart your phone or PC, somewhere in the heart of it will be a central processing unit, or CPU, connected to all the other devices that make it. Now, to show a really basic example, we're not going to use all those devices. The first one we are going to use is the clock. With every tick of the clock, our CPU goes through a step in what's called the fetch execute cycle, or fetch decode execute. This clock is slightly magic in that it ticks every time I click my fingers. In the CPU, I'm going to have 3 registers. These are bits of fast storage where the CPU holds values that it's working on right now. These are a register that keeps track of our instruction cycle, another that loads our instructions from memory, and an accumulator. The final thing we need in our simplified computer is somewhere to keep the instructions and any values that we end up calculating.
Memory.
That is RAM, random access memory, and we call it random access because it doesn't matter when or in what order the information is read or written. So that is our computer. Let's run a simple program. All it's going to do is count up. The processor has 3 steps: fetch, decode, execute. It will just repeat those on a loop. That's the one thing that's actually built into it. So we need some instructions, actually in memory. So let's load our program into RAM. That RAM is also used to store our answers, our outputs. In the real world, these would all be stored in binary, but let's not overcomplicate things right now. Let's keep them human readable. An instruction has 2 parts. The first part is the instruction itself, and the second part is usually a memory address. On each clock tick, the CPU will do one of 3 things. It will fetch that instruction from a memory address. It will decode that instruction, and it will execute that instruction round and round in a loop. So it's going to count up. We're going to begin with a number, add 1 to it over and over again. Fetch 1 prompting. The program counter is set to 0. So the CPU fetches the instruction at address 0 in the memory and puts it into the instruction register. Decode. The CPU decodes the instruction. The first part is instruction and the second part is a location. In our case, the instruction is load and the address is 6. So we will be loading the value of address 6 into the accumulator. Execute. The CPU executes this instruction. It takes the value of address 6 and loads it into the accumulator. In this case, the value is 1. The program counter is incremented. The CPU fetches the next instruction in the next bit of the memory. Decode. The CPU decodes the instruction. This time it's add, and the address is 7. So we'll be adding what's to address 7 into what is already in the accumulator. Execute. The CPU executes instruction. We add the value to address 7. And in this case, it's the value 1. 1 plus 1 is 2. Fetch. From the next memory location, number 2. Decode. An instruction to store is one of the foundations of computer science. So, execute. The program counter is now back at 1. The ability to jump, to loop, and to build instructions recursively is one of the foundations of computer science. So, we're back up there. Fetch from location 1. Decode. It's the add instruction again. Execute. 3. Execute. Fetch. Decode. Execute. We're in a loop, and we're counting upwards by 1 on every 6 clock cycle. Our program, with these simple instructions, doesn't have a halt command or any way to interrupt it, so it will just keep incrementing that value by 1 until the number becomes so large it can no longer be held by the memory address. How it breaks then? Well, that's a whole other video. I'm tired. This is a very fiddly way to program a computer. In theory, it can be done, but at this level, these instructions are just encoded in raw binary data, which is basically unreadable for humans. So we can convert that base 2 binary to base 16 hexadecimal. At that level, we call it machine code. The next step up from that is a symbolic language called assembly, which is a bit more readable, but it's still close to working that down. The original Prince of Persia game was completely programmed in assembly. That is almost unbelievable to painstakingly figuring out each pixel animation and encoding it into something that the computer almost understands directly. Programming like that is complex and hard and prone to the sort of human error that introduces massive security problems. It is difficult to code and difficult to debug. So rather than dealing with the messiness or, well, the pristine logic of machine code, higher level languages were developed as an intermediary step. Those languages handle all that memory reading and writing for us. So all we need to focus on is what we actually want the computer to do. So here's my code. Just the same instructions, phrased a little bit differently, phrased for humans to be able to read. I specify a variable, x. I then write a function that loops forever, and each passing through that loop, we increment x by 1. Once I've written that code, I then pass it to a compiler, which turns it into that original machine code for me. So when I run the program, it's loaded into memory and executed. If I want to run it on a completely different type of computer, a Mac instead of a PC, I can compile it for that CPU instead. But this still doesn't answer the question of how the computer is doing something as complex as decompressing and displaying this video. The answer to that is speed. At the speed I was clicking at the end there, we were executing one instruction every couple of seconds on one thread, one bit of the system. A modern CPU executes billions of instructions per second, gigahertz, on multiple threads. But at the heart of your PC or your phone, there is still just a ticking clock and a fetch, execute cycle. I've used a password manager for years.
I see. So the clock is very, very important, right?
Arithmetic and logic unit, which takes in binary numbers and performs calculations. And we've made 2 types of computer memory. Registers, small linear chunks of memory, useful for storing a single value. And then we scaled up and made some RAM, a larger bank of memory that can store a lot of numbers located at different addresses. Now it's time to put it all together and build ourselves the heart of any computer, but without any of the emotional baggage that comes with human hearts. For computers, this is the central processing unit, most commonly called CPU.
Okay, I'm gonna stop the video there. like the zoom there, because this shit is messing with my brain a bit, and I really want to lock in and focus the study. So, peace. See you tomorrow. Bye.